All right, so today we're going to talk a little about magnetic forces on charged particles. So that's going to be things like protons and electrons. We'll often talk about like ions too. So it could be, ionized helium or an oxygen beam or carbon beam or something like that. But the primary thing that you're going to hear about is mostly going to be protons and electrons. So the basic formula for the force on a charged particle from magnetism can be found using the equation F equals Q V cross B. So this is going to be a cross product. So if you guys should have learned about that in math class. So your force is a vector, your velocity is a vector, and your magnetic field is a vector. And so this is one of the ways we multiply vectors. So with cross products, what happens is that your force vector has to be perpendicular to both your velocity vector and your magnetic field vector. There's a couple other simpler ways we can write this that are less, a little less mathy. So we could say the magnitude of the force is equal to the charge times the magnitude of the velocity times the magnitude of the magnetic field. That was my dog. Say hi to Cicero. Times the sine of the angle between them. So that would be if I have something like your velocity is in this direction, your magnetic field is in this direction, your theta is there, right? So in this case, since those are both on the paper, my force would have to point out of the page, right? So this would be actually point down, so point into the page. So we can use either of these formulas are going to work for our purposes, really. But the sine theta is going to be really important for a lot of instances. Okay, so let's talk about what to do with this. How do we know the direction? So what we have is something called the right-hand rule. See, so that's enough, buddy. All right, so we have the right-hand rule. So what you're going to do is you're going to take your right hand, not your left. It's important to use your right hand. And I've labeled my right hand. Let's see if I can get it all on there. All right. So your palm is your magnetic field. Your fingers are your velocity. And your thumb is your force. So what I'm going to do is if I have, let's say, my magnetic field is going to go this way. So that's your magnetic field. And you have a charged particle, let's say a proton, going that way. Well, I'm going to take my hand, I'm going to take my palm, and I'm going to point it in the direction of the magnetic field, so that's going to be to the right. I'm going to take my fingers and point them in the direction of the velocity, so my palm's magnetic field, and so I'm going to do it like this. And my thumb is going to point in the direction of the force. So the force here is going to be into the page. So that's how I knew it was on this one too. I know that the velocities, the cross product's going to be, well, another way of looking at cross products, I guess, we should do is the force times the charge times the velocity that is perpendicular to the magnetic field, right? So what we're saying here is we're finding the component that's perpendicular. Another way of looking at that would be saying, if we have that example we had earlier, said your velocity is this way, your magnetic field is this way, right? So the component of my velocity that's perpendicular to my magnetic field would be this side, right? So I can take this vector, or maybe a better way of putting it would be this vector, right? That's the same one. So that, if that's my theta, well, and this hypotenuse here is V perpendicular is equal to V sine theta, right? So if I just take this theta and put it inside there, it's the same thing. So that's equal to Q times V sine theta times B. So it's the same thing. It's nothing different, nothing special. Yeah, okay. So a couple things we can do with this then. That we need to know about this. So I guess let's first talk about how do we indicate magnetic fields, because like all of the ones I've done so far, the magnetic field's gone to the right. And on this paper, I can easily do magnetic fields going to the right. It can go up, it can go left, it can go down, right? But what if it's pointing out of the page? What if it's pointing into the page, right? How do I draw that on my paper? And so what we do is we consider an arrow. So if I have an arrow, being good at art here, I'm going to spend a couple seconds, get a nice pretty arrow. Oh yeah, so good. What would you see if, so the arrow is like a force, because a vector is an arrow with a it's got magnitude and direction, so it's like an arrow. We can think like that. So if the arrow's coming towards you, coming out of the page, what do we see? Well, you're going to see a dot, right? You're going to see the tip of the arrow. So that's going to be out of the page. What about if the arrow is going into the page and it's going away from you? If it's going downward. So you're going to see the tail feathers of your arrow, so you're going to see an X. So that's going to be into page, will be an X, right? So we're going to use that notation. So let's consider a problem where I have, consider this scenario where I have a proton traveling into a magnetic field that's going into the page. So let's draw that real quick. So I'm going to draw a bunch of arrows to say this whole space has magnetic field that's going into the page. Actually, I probably need to draw more up here a little bit too, because what path is that proton going to take? Well, let's consider right as it enters this field, right? Its velocity hasn't changed, right? It's still that way. So what direction is the force on it? Well, we're going to use our right-hand rule, right? So once again, my fingers are the velocity, my thumb is the force, and my palm is the magnetic field. So if I take my hand, I'm going to have to put my palm down because the arrows are going into the page, and my fingers are going to point to the right. So what direction does my thumb point? My thumb's going to point up. So this is going to feel an upwards force, like that. You know, I'm going to go ahead and get a red pen, and let's put my force in red, like that. Okay. So now, a little while later, it's going to have traveled, to the side, kind of gone this way. So let's put it here for now, and let's say now it's curved, and my velocity is going to be in this direction, right? It should be the same length actually. Let's make that the same length because it hasn't slowed down. Because the force, the acceleration, is always perpendicular to the velocity, so it can't actually change the length of this vector. So what direction is my force now? Well, it's still going to be the same thing. I'm going to do the right-hand rule, put my hand like this, say it's going to be that way, and it's always perpendicular to the velocity, so it has to be that direction. And it's going to keep doing this. So the next one, I've run out of space here, so it's going to follow a circular path until it leaves the field. Which means that we're going to be able to circular motion stuff. So let's briefly review circular motion and briefly talk about that. So what are my formulas in circular motion? Well, I know that the net force, or the centripetal force, which isn't a special force, it's just what we call the net force in circular motion, is going to equal mass times centripetal acceleration, or more commonly what we call it is your mass times your tangential velocity squared over r. So now we're just going to replace this centripetal force term, this sigma force. We always say, well, let's replace it with what the forces are. Now the only force acting here is this magnetic force. So I can replace it with, well, what we did earlier, with QVB, QVB sine theta. right? So let's go ahead and do that. So it's going to be Q V B sine theta equals mv squared over r. So now I'm able to solve circular motion problems by getting to this equation. Now, if I'm solving for Q, I can divide both sides by this term here, VB sine theta, which, hey, actually what's going on here is everything's perpendicular. So what's my theta? Well, theta is 90 because the velocity is perpendicular to the field. So my theta is 90, so theta equals 90. This tells me that sine theta equals 0. Right? So now I just need to solve QVB equals mv squared over r. And look at that, I've got a v on both sides, so those guys are gone. So now my final equation I actually have to solve anything with is going to be QB equals mv over r. So most of the time you're going to be looking for like charge, or you're going to be looking for mass, or maybe velocity. I guess you could be looking for any of these. But we have 5 different variables here. You're obviously going to have to be able to know 3 at this point, or have some other way of finding them from something. But let's say you were asked to solve for what is the mass of the particle, right? You know it's got a charge of 1, let's say, and you can measure the radius as it goes through, and you know the magnetic field you're applying. So you're trying to, and you know the speed it's coming in with because you shot it in there. And you're looking for the mass. Well, we're just going to multiply by r, say Q B r, we're going to divide by v over v is equal to mass. And that's going to be how we're going to solve that problem. So now this is circular motion, right? So there's an important rule that AP loves to ask about. They love to ask about how much work does the magnetic force do in this situation. Well, because the velocity never changes, that means kinetic energy. Kinetic energy is constant, right? So how much work was done if the kinetic energy is constant? Well, work is the change in energy, right? So, and if kinetic energy is constant, this tells me that the work done and the change in energy is 0. All right, sounds good. I'll see you guys in the next video when we're going to talk about magnetic forces on current carrying wires.